Hi guys, Miss O'Connell here. So today we're going to be talking about center of mass. Okay, so what we mean by center of mass is that little dot that we've been drawing on our free body diagrams, right? We've been freeing our objects of their bodies, meaning that we are representing all of its mass concentrated at one single point. Technically, that point is called the center of mass of the object. Okay, so the center of mass is a point representing the mean position of matter, okay, of a body or a system. So it can be one object or multiple objects. So that point represents the mean, the average location of where the matter would be. Sometimes center of mass is called the mass-weighted center, but you do not want to define a word with the word itself. Okay, so basically average position of matter is a better representation of what center of mass is. We sometimes abbreviate center of mass as C.M. Okay, and naturally, if an object were to rotate, it would rotate about that fixed position, okay, its mass-weighted center. And again, on our free body diagrams, that dot that we've been drawing represents the position of an object's center of mass. So for normal geometric objects, the center of mass is usually at the center of that object. So for a circle or a wheel, it'd be right in the center. Okay, the object would rotate about that axis about the center of mass. For a triangle, it's a little bit more complicated to determine, but basically we would determine at what location the average matter would be located. And again, that dot is the same dot that we draw on our free body diagram. That position does not move, does not change, even when the object moves. Okay, so what we mean by that is if we have a rotating tire wheel, this position right here, the axle, is where the center of mass, aka the average position of matter for that wheel, is located. Even though the wheel is rotating, right, that position will not change, no matter how many miles you drive with your car on that wheel. Okay, so that position, the center of mass, will not change. So let's say we have something a little bit more complicated than a geometric object, or rigid body, we call it. Let's say that we have a system of particles. Okay, so if we have three different objects within a system, or three different particles within a system, the center of mass would most likely be somewhere in between them, right? So here's our system. We have three objects with mass. This position right here is our center of mass. If our entire system were to move to the left, to the right, okay, that position, the position of its center of mass, will not move. Okay, so if there's no external force within the system, this position will either move at a constant velocity or it will stay stationary. Okay, so for example, in the situation of an explosion, right? Two objects start together. That position for the center of mass will not change even when the objects move apart. Okay, that force is internal to the system. The force that causes the two components of the explosion to move apart are internal to the system. Therefore, the center of mass of the system will not change. Okay, so to get some idea, some intuition about where center of mass is located, you can actually click on this link in the PowerPoint that's posted in Classroom. So it's called the hang test. It's basically, it's a builder. It helps us find the center of mass of a system. Okay, so once you've opened that builder, pause the video and get to the builder if you have not. Okay, once you get to the builder, you can drag across the screen to create any object or system of objects. The center of mass will change accordingly depending on the amount of mass that you have in the system. Okay, so here we have 3 objects in our system. The center of mass, okay, the mass-weighted center, or the position where the average mass would be located, would be somewhere in between these 3 particles or objects. Okay, so for one object, center of mass is located in the mass-weighted center of that object. If we have 2 objects in our system, it's somewhere in between those 2 objects. If we have 3 objects in our system, it's somewhere in between those 3 objects. If we increase the mass, right, the average position would also alter. Okay, the hang test, if we take this little thumbtack here and we stick it into the object and we press go, the object is going to rotate. You see the object's moving, but the position for the center of mass is not moving, even when the object or system moves. Okay, so that position where the mass would on average be located will not change. And you'll see here that we can draw a straight line from the location in which the object had been rotating about, so that axis passes directly through the center of mass. So even if the object is non-uniform or the system is non-uniform, that system will still rotate about an axis according to the position of the center of mass. Okay, and you can play around with this and test it out. Okay, so equations for position of center of mass. If we are only on the x-axis, right, if all of our mass is concentrated along a x-axis or a thin rod, for example, we would take the x position of where, or the x-coordinate of where the mass is located, and we multiply it by the mass located at that position. We would sum the masses and the x-coordinates and divide by the total mass of the system. If we had an object that's sprawled across the x and the y-axis, meaning that it has surface area, we would then have to take the mass located at each y-coordinate, multiply the mass times that y-coordinate, and sum the masses and the y-coordinates, divide by the total mass of the system. So these 2 equations here give us the x and the y coordinates for the position of the center of mass on an xy coordinate plane. So take a second, pause the video, and write down these equations. Mass is always in kilograms. The coordinates x and y should be measured in meters. Okay, example 1. So here we have a one-dimensional system. So we see that okay, sorry about that. So we see that both particles in the system are located on the x-axis only, meaning that there is no significant surface area for either particle. So we're given the x-coordinates of both particles, okay, two separate masses. We want to find the center of mass. The first mass is 2 kilograms at the coordinate of 2 meters, and the second mass is 6 kilograms at the coordinate of 8. So we can guess, right? This object has more mass, so likely the position for the center of mass, where the average amount of matter would be located, should be closer to the 6 kilogram sphere. To find out exactly what that position is, we need to use the x-coordinate for the center of mass. So we take the individual masses and we multiply by their x-coordinates, divide by the total mass of the system. So we'll have here 2 kilograms times the x-coordinate 2 meters plus 6 kilograms times the x-coordinate of 8 meters. And then we're going to divide by the total mass of the system, which will be 8 kilograms. So we find that the position of the center of mass is 6.5 meters. So the x-coordinate, okay, would be 6.5 meters. So that would place the position of our center of mass, again, closer to the 6 kilogram mass, which we expected, okay, but in between the two individual masses. So this is the position of the center of mass of the system, this two-mass system. If this system were to rotate, it would rotate about this axis. Okay, so technically the coordinate, if we were asked for a coordinate, our coordinate would be 6.5, 0, right? Because there is no y coordinate to the center of mass. Okay, so let's take a look at an example where we are looking for center of mass in 2 dimensions. Okay, so we have more than 2 objects in a system. We need to figure out the center of mass. Okay, so in our xy coordinate plane here, we have 3 masses, 3 kilograms, 4 kilograms, and 1 kilogram. The 3 kilogram mass is located at 1, 2. So the x-coordinate is 1, the y-coordinate is 2. The 4 kilogram object is located at 5, 3. So 5 is our x-coordinate and 3 is our y-coordinate. Our third mass, or point particle, is located at 7, 1. Okay, and its mass is 1 kilogram. So take a second, pause the video, and I want you to predict, before we do the calculation, where you think the location for the center of mass for this 3-particle system would be. Okay, so you're probably thinking, right, here's the most massive object. So we know that the position of the center of mass should be closest to this object. Here's our second most massive object. Okay, but we do have mass below or to the right of these 2 objects. So center of mass is probably going to be somewhere around here. So closer to the 4 kilogram mass, takes into account that there is a 1 kilogram mass that has a significant x value, or x position. And let's do the calculation and we'll see. So first we'll start out by finding the x coordinate. Again, this system has a significant x and y coordinate value. So we need to find the position of the center of mass in both the x and the y and come up with a coordinate. So our x coordinate, we're going to take our masses and multiply by the x positions. So I have 3 kilograms times 1 meter plus 4 kilograms times 5 meters plus 1 kilogram times 7 meters, divided by the sum of the masses of the system. And we would get 8 kilograms. Notice here that our kilograms would actually cancel. Okay, and we're left with just meters. So our x-coordinate for the position of the center of mass is 3.75 meters. Okay, but we're not done. So we know that the x position is going to be, oh, this thing's in the way, is going to be somewhere around here. We need to find the y-coordinate to figure out exactly the position. So again, we take the masses and we multiply by the y-coordinates. We have 3 kilograms times 2 meters, plus 4 kilograms times 3 meters, plus 1 kilogram times 1 meter. And we divide by the total mass of the system, which is 8 kilograms. We find that the y-coordinate is 2.375. Okay, so the position for our center of mass is the coordinate 3.75, comma, 2.375. So if we were to place that on our xy coordinate plane, there is where it would be located. Okay, exactly where we had predicted. Closer to the 4 kilogram object. Okay, but takes into account that there is a 1 kilogram object that remains in the system, and that the 3 kilogram object has significant mass. Okay, so that is it for today. You can take a look at that Google form in Google Classroom, and please make sure that you watch the review and analysis of the virtual impulse lab and make corrections to any of the analysis questions. All right, have a great weekend, and I will talk to you on Monday.